Okay, good morning, students. Uh, I'm happy to show me myself is Selvaprakash. First of all, I would like to tell the program and other steps. This video lecture is conducting for special category SC students for their higher education and GATE preparations. Okay, now this is the time for to all know about me, myself, Selvaprakash, working as a assistant professor in chemical engineering department, Erode Sengunthar Engineering College, Perundurai, Tamil Nadu. This is the most valuable time for yours. Actually, I'm not that much interested in the topic, but this is the most important topic in always chemical engineering department. Okay, the topic is reactor design. Uh, you all know about the basics, basic things like CRE. CRE have two different papers. CRE 1, 2. Okay, this difference between what is the engineering and what is technology. Okay, the simple application of science is engineering. Okay, just remember the simple application of technology is engineering. Okay, there is two lines you have to remember. First one is simple application of science is engineering. Okay, and then simple application of science is technology. That's it. Further, I'm going to discuss in this video lecture, thoroughly in reactor design only. Okay. Okay. We have to know before that we have to all know about the what is ideal and real. Okay. Ideal means is the perfect stuff. Anything else means any there is any process or there is any reaction or you can consider as anything if it is perfect, if it is perfectly scheduled as per the times or like things. Okay, steps is ideal. Ideal means perfect. There is a straight line process. Okay, and real is what is meant by real. In that we all know about real is how do I tell that which is there is the one operating condition or process control. According to that, the process will run. That is real. Real means there is an operating condition is here. According to this, the product or the process will run. Simple. Okay. Okay. In ideal, we have two types. One is PFR, which means plug flow reactor, and second type is CSTR. CSTR means there is a simple technique in that name. Okay, what is meant by simple? Simply we understand in the name only, which is CSTR means C means continuously. That's a process continuously. CS means stirred. There is a stirred equipment is used. Okay, T means tank, and R means reactor. We now accumulate the wordings. Continuous stirred tank reactor. Okay, this is the one we have to study the deep level and use it mostly used in the industries, which is CSTR. Okay. Real. In these materials, I already told real means there is a process which having the operating conditions or the specified conditions. Okay, like this in this slide also, I put the wordings. Unique designs geometrical and therefore RTD measurements, which means that there is a RTD measurement, which is residential time distribution. Residential time distribution means in the reactor, we all know about the feed. The feed is given and the reactor runs or the process runs. Finally, we all get the product. Okay, like that only there is a RTD process includes, which means residential time distribution. That is how the time, how much time taken in the process. Okay, how much time taken inside the reactor. That is the reactor. Sorry, that is the RTD, residence time distribution. Okay, in this residence time distribution, we all must know about the multi-phase or single phase. Yeah, we already know the basics about the multi-phase and the single phase. A multi-phase system there is a more than two phases used in the reaction. A single phase is the one leak single as well, which means gases. Gases means gaseous, or liquid means liquid types reactors or reactions or process involved in this single phase reactor. Okay. Variation of momentum mass heat transfer. In this, as I told him, we as I told in this video lecture, we all know about the reactor designs. Okay. In the reactor designs, there is a some steps we have to concentrate on the reactor design. What are that? One, momentum, and the second one, mass, and third one, heat transfer. Automatically you ask the question, why we have to concentrate on the momentum, mass, heat transfer in the reactor design? There is a name, reactor design. There is a name, reactor designs. You already know about the reactor design means there is a design like drawing steps or the measurements are included in the reactor design. But as you thought, that's not like that. We have to concentrate and fully know about that heat transfer, mass transfer, momentum, and how the equipments are designed and what is the process operating times. We have to study all the steps about in the reactor design. Okay. Now I have to tell the momentum. You all know about the there is a big changes happened in the process that is known as the momentum. So how this momentum affect the reactor design or reactor? When we give the feed, automatically we initially we check the initial conditions, which means operating conditions. Already we all set the operating conditions. Okay, for the operating conditions, how the feed react to the or react or convert to the product. Okay. According to the reacting conditions, how they feed convert into the product is the matter we have to concentrate. In that, we have to analyze the momentum. Momentum is nothing but which we have to analyze the big changes or small changes. Mostly we in this momentum and reactor design topics we have to concentrate on the big changes happened in the process. Okay, which is momentum. Likewise, we have to analyze the operating conditions where the momentum happened in the reaction process. Okay, where the momentum happened in the reaction process. In that we have to concentrate. Okay, as next that second one is first one is momentum, which is clearly explained. Now you have any doubts, you can ask after the class section. The second one is mass transfer. In the mass transfer, we have to study the how the mass, okay, how the mass transferred, how the mass transferred in the reactions, okay, will happen when the reactor or reaction happening, how the mass transferred into the different states. Okay, we all know about the reaction, reactor, process, like kind of stuff. Basically, we have to take for an example 100 kg of feed converted into the 75 percentage of product and 25 percentage of side product or recycled product. That is none of business for us. Now, and now we consider the third one. What is the third one? Heat transfer. Likewise, the same mass transfer, heat transfer also study. What is heat transfer? How the transfer of heat studied in the reactor is the transfer. Okay. Okay, just for a recall, in this slide we saw the what are the reactor types and what is mean by real and what is mean by ideal. What is the ideal reactor types? PFR, plug flow reactors, ESTR, continuous sterile tank reactor. And introduction. What are the things we have to study for the reactor design? Okay. Second, in the reactor design, mm, before that we all know about the industries. Okay. In the, for example, take the chemical industries. One of the chemical in pharma industry. Okay, chemical pharma industry. I would like to tell the basic basic or fundamental thing of the industry. Okay. In the industries, what is their aim? What is their aim? If anyone knows, tell me. In the industries, all the industries are all the industries are mainly concentrated on their profits only. Profit means it's money based. Okay. According to that profit, they have to reduce the reactor cost or labor cost, like that expenses. We have to reduce the expenses for profits. Okay. In this reactor design, how we can reduce the expenses for the reactor cost in that reactor, how the cost cut happened means PFR, for a PFR reactor we have to look at the pressure vessel terms. Okay, in the pressure vessel terms we have make some changes for a for cost cut process. Okay, next step. Okay, in that PFR is first one, second one CSTR. For CSTR, how can the happen, which is reduce the cost or cost cut process? The storage tank with mixture storage tank with mixture in the tank we can reduce the some parts with some steroid equipments or mixture terms. We can reduce in it, or we can make a small changes or little bit alterations in that we all reduce the cost for a CSTR. Okay, next, what is the other? If this, the storage tank is fully prepared, there is no changes for the storage tank in CSTR, which means in the terms, we automatically move to the next one, which is pressure vessel. How the pressure in the pressure vessel, how we can reduce the cost in the CSTRs? Pressure vessel is the very important one. Why? Because then you guys already know about the basic steps of the reactor or process is what which is operating conditions. In the operating conditions, there is a major roles played by the pressure and the temperature. Okay. Likewise, in the CSTR, which is continuous fluid tank reactor, also pressure vessel is playing the major roles. What is that? Hydrostatic head give the pressure to listen. In the in simply, I can say that the pressure of the pressure for the CSTR continuous fluid tank reactor is given by the hydrostatic head for the equipment. Okay. In that process or in the hydrostatic head design process, we have to cut our expenses by easily. In that slide, reactor cost slide, I have to tell them how we all cut the price, how we all reduce the amount for the profit. A simple recall of this slide is the FR and CSR, how we can cut the cost or reduce the amount, reduce the reactor cost. Okay. Okay. Now the second one is reactor cost. Yeah, another major important. In the previous slide, we also saw the basic concept of the reactor cost. Reactor cost. In this slide, we all are going to study about how we can adjust or alter the reactor volume from the reactor kinetics, and in that process also we can reduce the cost. Okay, as usually the ultimate aim is reduce the cost of the process. Okay, for that we have to reduce the reactor volume. Okay, if I can change the reactor volume means if the cost cut, automatically the amount of the process becomes low. It is it is possible or it is practical. If I alter the reactor volume, automatically what will happen? The process will affect. Okay, this is not unfair. This is not unfair. We have to check the product. We have to check the product quantity and also quality. For that, we have to analyze the reactor kinetics. Okay, we have to analyze the reactor kinetics. Why we have to analyze the reactor kinetics? This is simple. We already know if I reduce the reactor volume, automatically the reactor cost will become low. This is simple. Why I did not choose the process? Why I did not choose the process? Which means there is a one negative point is there. What is that? The reactor volume become low means the product quantity and automatically quality become low. Okay, this is not one. This is not all industries want. Already, as I told initially, all industries need the higher profit levels. Okay, as I told initially, all industries want higher profit levels. For that, we have to design the reactor. This is the major important problem or difficulty in the chemical industries. Okay, for that, reduce the reactor volume does not affect the product. There is a simple method is here that is Hope stress formula. It is I don't know whether you already know about the Hope stress formula or not. This is used for the wall thickness terms. Initially I told it there is a in reactor design there is simply not the drawings or measurements. It's all about the heat and mass transfer and moment. Okay. We have to analyze the wall thickness by using the Hope stress formula. Okay, in the you all see the formula in this slide. P equal to PR divided by SE minus 0.6 P whole plus P small c. Okay. Now I am going to explain the notations. T is the vessel wall thickness. Thickness means T. Okay. And the second one is P. P is pressure, which is design pressure difference between the inside and outside of the vessel. Okay, PSI, the unit of PSI. And R, which is denoted as the inside radius of the steel vessel. Okay, then S is the maximum stress for a steel. Okay, why we using the steel in the reactor means if the react if the reactor was built by the steel, we have to analyze the what is the minimum amount of stress allowed in the reactor and the maximum amount of stress allowed in the reactor. Okay, and now the E is denoted as the joint efficiency. Efficiency means we have to calculate initially according to the reactor designs. Okay, in that for that formula we can assume approximately 0.9. Okay, again, next one is TC. Allowance. What is the allowance of the corrosion? Corrosion is automatically there is in steel and a liquid, so there is the chance to made a corrosion. There is a chance automatically to made a corrosion. So we have to analyze the corrosion allowance, which is automatically assumed for the formula 0.125. Next slide. As I told previously, we have to study the pressure vessels to reduce the reactor cost. There is a formula used in how we have reduced the pressure vessel. Okay, this is considered as this is the question. How we reduce the reactor cost by using the pressure vessel. Okay, already I told you have to consider that material, construction material, and then vessel, mass of the vessel, pressure of the vessel. Like that. Simply, we, we can understand the reactor cost things by using or by reducing the process of pressure vessels by using the reactor kinetics. Okay, okay. The first, the starting part of the reactor design over. Next, we have to analyze the reactors in the process simulations. Simulations is a little bit interesting and a problematic topic in the reactor designs, or which is subject to simulations and stoichiometric models are the hardest things. As I already told, two models. One is multi-phase model and a single phase model. The chemical equilibriums. Before that, you have to know about the reactors and the reactor design. Okay. You guys already know about the thermodynamics second law. The second law, there is a statement which is we did not get the 100% of the process. Whatever it is, we did not get the 100%. That is the simple statement of this law. As that we did not get the 100% results in the reactor designs also. Okay. For that, we have to make some assumptions. Basically, I would like to tell you that you have to assume the measurement or phase or how the reactor runs and like the operating conditions. Okay, like that. We have to assume the basic steps. After that, only we can simply approach the problem or reactor design, whatever it is. Okay. This is the basic one. We have to assume some things for reduce the difficulty of the problem or design process. Okay. Kinetic model. Okay, you guys just remember or not? I don't know. Previously, in the two slides before, I told it we have to reduce the reactor volume by using the reactor kinetics. Okay. In the kinetics things, we have to know about the kinetics models. There is some models, formulas, or standards used for the CSTR and PFR or custom made models, which is multi-reactors. There is two or more reactors used. The one is CSTR and the another one is PFR and the another one is CSTR. For that, for that reactors, we have to assume some custom models. Get some custom model. The, you already know about this three reactor types in that slide. Okay, what are the kinetics models? Okay, as I told you, what are the kinetics models used for the reactor design? Us and CSTR PFR. Before that, we have to consider the two important factors in the kinetics reactor kinetics. Okay. The first one is size of the reactor, volume of the reactor, how much mass can fit into the reactor, given into the reactor. Okay. And the second one is what is the dynamic, what is the dynamics of the reactor, or else I can simply told what is the process, how the reactor runs, what they need, which is how to set the operating conditions, how to set the operating conditions for the reactor dynamics. Okay. Before that, this, as we saw in the previous slide, the two important things, size of the reactor and the dynamics of the reactor is the very important one. According to the CSTR, BFR, multiple things. Okay. Before that, before that, in this BFR, before that, in the BFR reactor, there is a back mixing terms are frequently used at the time. At the time, you guys know about it. What is back mixing? Automatically, you have some enthusiasm to know about what is the back mixing, why this is used. Okay, why this is used. For that, we have to we have to already know about that mixing. In the CSTR, I already told you that is a sterile equipment. That's a sterile equipment was using to make the proper mixing or uniform mixing. Okay. If there is no uniform mixing, what will happen? There is a reactor and there is a process, there is a field. As per the guidance, we all give the field operating conditions, but we did not get the proper product as per the guidance. What is the problem? Automatically, we came to know there is a problem in mixing inside the reactor. So, what is happened inside the reactor? Okay. We have to analyze the how the mixing happened. What are the ways? What are the ways the heat converted into the reactor? Automatically, we came to know about the analyzing the reactor kinetics. The back mixing is the major important process inside the reactor, which is there is a corner, okay, two or three, four corners inside the reactor. In the corners, how the reactor or how the reaction happened, which is nothing. How the feed converted into the product. This is the simple. We have to analyze the how the feed converted into the product by using the back mix. What is the major thing in the back mixing? Which is In the reactor, there is corners. The reactor, there is corners. At the corners, how the feed converted into the product is the simple concept. Okay. As I previously told you, the reactor, there is a reactor kinetics. In the reactor kinetics, there is a two major factors played in the played in major role in the reactor. One is reactor size, and the next one is reactor dynamics. Okay. Now you all guys listen very carefully. We and just tell the formula. I want to before that I want to clarify the is the slide is visible to all or not. Okay. Check your net connections and if there is any difficulties after the class, you all guys tell. We will rectify the next section. Okay. Okay, I'm going to now pronounce the formula. If you need any, you need write it. Okay. B equal to F small k o integral limits 0 to x k and then dx divided by minus r k. Array rate equation is nothing how the reaction happened for the given operating conditions. Or else I can simply tell that how the reactor measured, how the reaction measures. For that, the rate equations are used. Okay. The next one is space time. The reactor, we already know about the basics. In the basics, we already know about the operating conditions. In the operating conditions, there is nothing bigger than the pressure and temperature. Okay. But in the temperature and pressure, or in the operating or other operating things, the space time is played a major role. Okay. In that, what is the space time? Automatically, we ask the question: what is the space time? Space time is nothing at the specified condition how the reactor performs at the specified condition how the reactor performs according to their volumes is the space time. Okay. And next, what is the next factor we have to consider in the reactor design is outlet conversion. In the reactor design or reactor kinetics, there is a conversion played a major role. We have to must analyze that how much conversion happened at the operating conditions. Okay. But as we saw previously, there is no back mixing in the PFR reactor. So automatically the PFR and the reactor kinetics reactor process is become easy. because there is no back mixing. This ESTR, complete back mixing is happened for all the reactions. At the time, we have to consider two factors. As I told you previously, size of the reactor and outlet conversion. Okay. Simply we can understand by seeing the slides. There is a formula change. We have no back mixing. We see the V form, see the V and the CSTR in the CSTR complete back mixing. For V, see the formula. But the reactor terms, as I told you previously, there is a multi-phase and a single-phase reactions happen. Okay, in that multi-phase and the single-phase reactors, there is some kind of types used. After that, only we can understand the reactor types. Basically, okay, there is a four types. One is bulk fluid, and the second one is external surface of the catalytic pellet, and the third one is internal surface of the catalytic pellet, and the fourth one is how the catalytic surface have reacts according to the reactant. In the slide, you guys see there a reactant at the top of the slide. Okay. So this is how the reactor, this is how the reaction happens in the reactor. Okay. Automatically, you can understand the catalytic pellets, external and internal surface, how the concentration of the B, which is inside the reactor concentration, inside the reactor, feeded or a catalytic named as B. Okay. Listen the slide and you can guys easily can understand this process. For the next slide, so this is the in depth of the what will happen in the reactors. If we already know the reactant A converted into the B, simply we all know about the thing. But see the slide how the major simple steps fully happened in the reactor. There is a major 7 steps involved in this bulk fluid catalytic reactor. Okay, the first one is external distribution, which is where U1 feed A is transferred into the external surface of catalytic pellet. Okay, this is the external distribution rate AC. There is a concentration change, so that we have to mention the difference in concentration. The next one is effectiveness factor. The effectiveness factor is nothing what how the field A is transferred into internal surface of the catalytic pellet from external surface of the catalytic. Okay. Now the third one is surface absorption. Simply you all know about the absorption in the terms where that our initial field A under the catalytic S react and to form some intermediate product which is named as here AS. Okay. The final converted converted product will made in the surface reactant. Okay, A gives B. Finally, B for the B product. In the product, there is some intermediate products will attach. For that, we have to do a resorption process. Okay. The next sixth one, diffusion of products from interior to core mouth. This is the sixth one. There is nothing. You guys just remember the sixth and seventh process is simply diffusion. Just remember the diffusion. Okay. But you guys understand the how or which the product be diffused through the intermediate and the core mouth and the bulk. Okay, this is just nothing, just a reverse process. Okay. Okay. As I previously told, there is a catalytic reactor. In that, you guys know about the still you guys know about the how the reactor happened inside the reactor, how the reaction happened inside the reactor. There is a four mechanisms here for the catalytic reactor. The first one is surface reaction limiting, and the surface absorption limiting. The next one is surface desorption limiting. The final one is combination. Okay. As you guys have completed your schooling. After that only you can join the engineering. In your schooling, you must study about the nanometer isothermal. Because remember, you have to remember, lanyard mechanism is the basic one. For that, we have to simply understand that catalytic reactors and how the reaction happened in the catalytic reactor. Okay. Okay. In the video lecture, I have to ask some basic details. or else you guys first complete the full video. After that, I have to automatically after that I have to ask some questions because after that only I can understand how you guys understand my video. Okay. Still now we still now we saw about the catalytic reactors. Automatically in the catalytic reactors, enzyme catalysis enzymes are played in the major roles. Okay. For that we have to, as I told before, we have to analyze the kinetics, kinetics, or nothing. Design is nothing. It's all about the kinetics. Okay. What is the enzyme kinetics? For the way on the trap before slide, I talk about the line isotherm. You guys are remember or not? Just go through and check it. Check it. In this one, we have denoted the enzyme kinetics as an RS. Okay. S is the substract, which is nothing the reactant. Okay. Enzyme is E. Enzyme is denoted as the E, which is catalyzed. Catalyzed. Okay. Okay. Overall, in till now, I talked about the basics and then heat and mass transfer, momentum, kinetics, and the pressure volume. In how the reactors meet their operating conditions, space velocity, and the linear isothermal, all the things, problems. What is the disadvantages of the reactor designs? Okay, in the reactor designs, managing heat is the biggest problem. Okay, we have to reduce the heat, or else we have to convert the other useful products by using the heat. And the final one is optimization. Uh, you, you guys all heard about the word optimization, but in the reactor or reactor kinetics, what is the optimization? Is nothing but how full amount of heat converted into the product. Okay. How the full amount of heat converted into the product is the optimization. For the desired product, we have to optimize the some factors inside the reactor. The one is relation, sorry, reaction network. We have to must change the reaction networks for maximize the yield and maximize the selectivity and maximize the attaining region. Okay, okay. The first point of the maximizing the heat effect is reactions run away, reaction dies, preventing the explosions and preventing stallings. Okay. You guys are very familiar with the endothermic exothermic reactions. In the terms, we all know, we all discuss about the heat effect. Heat effect. Heat effect. You have to ask the question: what is the heat effects? You guys already, you guys always tell about the heat effects. Heat effects. The heat effect is nothing but the temperature difference in the reactor heat effects. Okay, in the temperature change happened in two major things, two major places. One is on equilibrium, the next one is on kinetics. This is the simple temperature difference based on the single equilibrium. Okay, for an for an increment of temperature, incre- increment of temperature, we have to consider the rise of endothermic reactions and the drop of exothermic reactions. Okay, till now we are discussing about the basic negatives of the reactor design. Automatically, what will happen to the unfavorable equilibriums happen? One is reversible exothermic, and a reversible endothermic. As you guys already know about that, XA is the conversion and T is the temperature. Just listen the slide and understand the graphical representation of the irreversible and reversible endothermic exothermic reactions. Okay. Simply, we can remember the things by understanding them. Increasing temperature automatically increase the rate. Okay. The next part is equilibrium limits automatically control the conversions. Before the temperature or the heat effects or equilibrium or kinetics, we have to study about the what is the nature of the field. Nature of the field, the first major thing is temperature. What is the temperature of the field? The next one is if the reactor field is highly highly non-reactable. At the time we have to use the heating or cooling terms for to convert the reactable from non-reactable. Okay. In the video lecture, I have to tell the what is the basic engineering tricks. What is the basic engineering tricks in the reactor design? Okay, there is a four major points I have to discuss in the topic of reactor design. Okay, the first one is what type of reactor we use, and the second one is feed point. Okay, there is a single feed point or multiple feed point. Okay, the third one is dilutes. What type of feed nature is playing the major role? As I told, the dilutes are also becoming the category one. Okay. The last one is temperature management with heating or cooling to convert the non-reactable feed into the reactable food. Sorry, feed. Okay. Okay, guys. Thank you. This is the basic concepts of the reactor design in CRE. Thank you. Thank you all. Thank you for your cooperation.